Okay, so today in very low, what we are going to design is a ALU. So the specifications could be various, but yeah, for our problem, the specification is something like this: that there are 8 operations which are supported by my ALU: add operations, subtract, increment, compare. So these 4 are arithmetic operations, and these 4 are logical operations: logical and, logical or bitwise and, bitwise or, bitwise or, and bitwise not. So total 8 operations are there. To have 8 operations, we would require opcode which would be of 3-bit byte. So 3-bit of opcodes are required, and let me say that opcode 0, when opcode 0 is there, then it is add. Opcode 1 is there, then it is subtract. Opcode 2 means increment. Opcode 3 is compare. Opcode 4 is and opcode 5 is or, so on and so forth. So this is about opcode. And what about the inputs and outputs? Let's say if add is there, A and B are the input, Z is the output. For similarly subtract and or XOR, A and B are the inputs, Z is the output. For increment, only A is the input, B is not the input, and Z is the output. And for compare, A and B, this is again a typo, A and B both are the inputs, and LT and GE, less than and greater than equal to, are the outputs. Okay, and in case of not, only A is the input and Z is the output. So if these are my inputs and outputs, now I can design the block diagram. I know the functionality based on the specifications. Specifications are clear enough to tell me the functionality. So input output is, I would have A and B as the input, opcode as the input, and Z is the output, and the 3 more output are LT, GE, and carry. So there was no carry here, but I added carry as an additional output so that it can be useful for let's say add operations or subtract operations. Now the width of these operations A, B, and Z, let us say they are n bit wide. What is the value of n? It could be 4, it could be 8, it could be 32. Let me consider that it's a generic value of n. And opcode is always 3-bit wide, and LT, GE, and carry, they're all single bit. So if I have to design such kind of a circuit, there are 2 challenges. One, that I need to do all these operations, okay, and I would like to do it efficiently. So the second thing is, there would be 8 outputs which are produced. Now all of these 8 we have to send to only.
इस क्वेश्चन का आंसर के लिए कर रहे हैं ब्रेक कर दिया था नहीं कर रहा किया नहीं बोल रहा है कि उसका मुझको बोल देना कि जैसे ही वो दूसरा बदल गया अपना पॉइंट दूसरा पॉइंट बोला नाउ आई एम स्टार्टिंग
Please mute yourself.
ये तो क्या सर इनको मेरे को कंपाइल करने के लिए पूरे को लाके फिर ट्रिम करना और टुकड़े टुकड़े करना और इसमें मुझे 2 घंटे लगते हैं
yes, please mute yourself. Thank you. So there are 2 challenges. One, we have to design it in an efficient manner so that less hardware is consumed. The second is, there would be 8 outputs, but finally we have to send only 1 output. So most likely we can use a good multiplexer. Okay, so let's see how to do this. Now the first part, doing it efficiently. So we see that all these 4 operations, add, subtract, increment, and compare, all of them can be done using addition, using one adder. Okay, so for example, I can write A plus B as an adder, and similarly, if I want to subtract A minus B, I want to subtract from A, so I can take 2's complement of B. And if I want to take 2's complement of B, it is essentially not of B and then plus 1. So these 2's complement of B. So then this is essentially an addition operation, plus 1. Okay. So increment is A plus 1. There is no B involved. And in comparison, again, I can use subtraction. I can say if A is less than B, if A is less than B, my output is going to be negative. If A is more than B, my output is never going to be out. If A is more than B, then my output will be always positive. Okay, so because it's a subtract operation, so I can simply use 2's complement here, and yeah. So here I can further see there is a lot of places where 1 is involved, so I have to do +1 +1 +1 in at least these 3 operations. So what I can do is I can use C in of an adder, which was not specified as an input here. So, but this addition, if we are using any generic adder, that adder will also have a C in as an input. So this C in I can use as 1 if I want to add 1. So this way it could be an efficient and interesting utilization of this +1 without requiring any additional hardware. So I can summarize what I'm saying. So essentially I can say that I need to do increment. So I need to do increment if the second operation is 0, else it is B. So sorry. So if I need to do increment, then the second operation is 0. Otherwise, second operand is always B. So in case of increment, then I have to made second operand as 0. Okay. So I can also see if I need to do either subtract or I'm comparing, then I also need to invert the second operand. So B I need to make as a B inverse. And if it is add, then C in is equal to 0. Otherwise, in all the other 3 cases, C in is equal to 1 here, here as well as here. Okay. So this is how I can use the same adder. If I put these 3 additional conditions, then I would be able to utilize the same adder. Okay, so this was about adder. Now the second thing is, yeah. The second thing is how multiple operations and the single output is possible. So here we have to use mux. There is no choice about that. But in mux, there is now one challenge that my opcode, which was a 3-bit opcode, I can either use that as a control signal, or there could be a sort of one hot encoding which I can use here also. So why I need to use one hot encoding? Because see, when I'm using this addition like this, then the values, the meaning of those 4 has either they would require to be demultiplexed here based on the control input, or I can use this one hot encoding. In case of one hot encoding, what I can say is, let's say as it was discussed before. So if it is, for example, is add is 1, and then whatever is the add result, I can do an AND operation with that. And similarly, if the other operation is AND operation, so similarly there would be 8 such operations. We can identify that operation and can AND it with that. Okay, and then finally OR all of them. Now one thing we have to understand is that this AND operation, so this is add would be a logical 1, or it would be a single bit, but this result is usually n bit wide. So we have to make something which is kind of a replicate operator, so that if it is 1, then it could become n bit 1. Okay, so we'll see that in demo. So one thing you will notice when you will see this particular demo, that the design is done using a data flow. Okay, so when we are designing in Verilog, there are 3 ways of designing. Either we can do data flow modeling, or we can do structural modeling, or we can do behavior modeling. So when we are using behavior modeling, then we are not sure what is going to be the hardware result. So if we are trying to model the hardware, we want to know what eventually will be there in hardware. Either we should use structural model or a data flow model. So for that purpose, I have used here only the data flow model plus some bit of structure, because we are instantiating header. So I am starting with whatever code we have written yesterday. So we have written full adder, that has been explained. Full adder n was also explained, so which was a n-bit generic full adder. And now we are also building upon that. We are also designing an ALU, which is again generic ALU, which could be of any particular bit width. So the input, as it was mentioned in the problem statement, we have A, B opcode as the input, Z is the output, L, E, LT greater than equal to, and carry, these are the outputs. So we mention n-1 colon 0 as A and B as the input, and then opcode is 3-bit, and Z is also n-bit, LT, GE, and carry, they're all 1-bit. So first we do is a decoding part. So in decoding, we try to identify whether it is add, is subtract. So if you see this particular logic, so this is essentially a decoder. So where inputs are 3, and based on the 3 inputs, we are generating 8 outputs. So now we have written the standard decoder manually. Okay, so in this manual writing, we have, this is 000, then we had 001, 010. So similarly, all the conditions has been enumerated. They are simple decoder implementation in our data. Now, because we would like to use reuse our adder, so we created another couple of intermediate variables. So to say that if we need to invert, and if we remember, invert would be there, B would be inverted if it is subtract or if it is comparison. Okay, so here we use this conditional operator. So which this conditional operator say that if B invert is 1, then B would be inverted. If B invert is 0, then B would be as it is assigned to B. So B invert is another n-bit signal. So this way we have used this conditional assignment operator. So you remember, you see that there is no case statement, there is no if-else statement. Case statement and if-else statement are possible only and only in behavior model. In our data flow model and structural model, we do not use if-else statement. We do not use case statement. So here the alternative of if-else statement is this conditional operator, which is assigning, this is a small multiplexer. This is a 2:1 multiplexer. This is a single control bit, and based on this control bit, it is sending either this or this. So 2:1 multiplexer would be implemented if we are using this conditional operator. So similarly, second operator we need to find out. So second operator either would be 0 or it would be B invert. So if increment is there, if it is increment, then we have to say the second operator is 0. And to say 0, what we have done, this is a replication operator. So in this replication operator, we said 1-bit 0 would be replicated n times. So in a replication operator, we do a curly braces, the number of times we need to replicate, and then what need to be replicated. Here, what need to be replicated is 0, 1-bit 0, and it need to be replicated n times. So this is a replication operator. So this means n zeros, either it will select n zeros or it will select B invert. So whenever we are doing assignment, it is a duty of designer to match the number of bits which we are assigning from left hand side to right hand side. Otherwise, sometimes Verilog will not give error, but your design will finally give error, will show error which would be difficult to do. Okay, so similarly, we'll also find out Cin. Cin, if is add is there, then it is Cin is 0, else it is 1. So one of the side effect of this would be that for is add, is and, so basically opcode 5, 6, 7, 8 also my Cin would be 1, but I don't mind because finally my value will not pass further. Now I instantiate my full adder n, which is a generic n bit adder, and I assign a second operator, second operand, C in ZT adder. So ZT is a Z temporary adder that I am assigning as output, and C out. So this, there is some problem here. It should have been actually ZT adder for n minus 1, and similarly this is also inverse of ZT adder n minus 1. So this is essentially we are catching the sign bit for the MSB of my adder, whether it is high or whether it is low. If it is high, that means the value is greater than, that means value is positive. If it is 1, that means value is less than. If any of these 4 operations are there, then we are using the adder. Now, logical operators are easy. We can simply use A or B, A and B, A, XOR B, and inverse of A. Okay, so this part is essentially my one hot encoded multiplexer. So here what we are doing is my adder would be ended to, if my use adder is 1, then the output of Z adder would be, ZT adder would be passed to Z adder, otherwise it would be 0. Similarly, if is or is 1, then only ZT or would be passed to Z or, otherwise it would be 0. Okay, so uh, because there is only one opcode, because of that, only one of them will have certain value, all of them, all of them will have 0 values. So this way, I can simply OR all of them to get my output Z. Yep. So you can see this way we can design this whole ALU. Again, I would, if you will read these lines, they are essentially some of the relations of, if we are using some library, we could have directly used these multiplexers or decoder modules. Here we have used decoder here and multiplexer here. Otherwise, because I was not using any library, so I have to write it myself in this module, and so that's why it looks little more complicated than a typical ALU. So whenever you will see into internet and you would like to search for ALU design, the mostly what they will do is they will create a data flow model of the ALU. The data flow model of the ALU has, again, I'll say the major challenge that we don't know that whether how many adders they are using, how much would be the delay. We don't know the internals, how synthesis would result in that particular ALU. But if we are using data flow modeling, then data flow modeling will make sure that whatever we are doing, we know that how many AND gates and OR gates would be there. Okay, so again, for test bench is more or less straightforward for this. I used the previous test bench where we have created duty here, and we created register for inputs. Test A, test B, test of code are the inputs, and test Z, and these are the wires. Def param we are keeping as 8, so that means my whole design is a 8-bit. And then ALU would be instantiated here, and in the initial I am asking for some 10 different values, where test A and test B both are 256, means 8-bit wide, and I can have opcode which is 0 to 7. And like always, we are also monitoring all these values, and also we are dumping the file in VCD. So if we save and let's say if we run, then what would happen? Yeah. So if I'm running it, then I see that, let's say I am putting the radix equal to binary, and then if I see, let me put test upward little higher so I can compare. Similarly, Z also I can push little up. So if it is 5 means actually an OR gate. So if I'm doing an OR operation, the output has to be 1, 1, 1, 0, 0, 1, 1. So it's coming out precisely correct. Similarly, for 1, it is a subtraction. You see there are some delays also being introduced. The delays are there because we are using our ALU, n-bit ALU, which has those delays embedded there. So you see it's a small number, A is a small number, B is a big number. So when we are subtracting B from A, then it comes out to be a negative number. Okay, so this is 1 0 is also an addition operation, so my output is there. So similarly, if we would like to check my output would be correct in most of the cases, in all of the cases, and this is the way we can design and test. So for better testing, we have to write always the focused test cases, focused so that we can see all the scenarios. So for example, here we should have at least written one test case for all the 8 scenarios, and that would have given us a more confidence in our design. Okay, so with this, we are done with the demo, and I would be back with you if you have any questions.